So let's talk about some examples for how to apply LIME actually. So as learning goals, we see some real-world data examples, real-world in the sense what normally machine learning practitioners use as exemplary data. And we see also how we can apply it to image and text data. So as we discussed before, we're using here the credit data set. And let's say we now having an SVM with an RBF kernel, which could lead actually to a very complex model, right, because of the RBF kernel. And we have data point, and that gives us actually that we get a bad scoring for our credit application of more than 60%. So most likely the bank will reject us. The will be our training data as before, and we're using the Gower proximity actually as a metric on this mixed feature set. As so we had model class, we were using the L1 regularized model with 5 features actually. So we'd like to reduce it a bit. And here we see the original point we'd like to explain. So saying, okay, age was 22, female, was having 2 jobs, I believe, has his own housing already, nevertheless, has little savings, moderate checking, credit amount, duration, what she's asking actually for, and what is actually the purpose for having the credit. Good. Now we can actually put that into LIME, and what we would like to get is maybe something like that. So we see now that first of all we're focusing on 5 of our features, not on all of them. So we have a local model, linear model, here linear form, but saying okay, only 5 of our weights are allowed to be non-zero. We see also that actually the score is very similar to our original one, so at least that's well done. We can also compute the local fidelity, which would lead into that kind of number, where we use the Gower proximity and also for the loss directly actually Euclidean distance, so L2 loss. So coming back actually to the nice graphic, we see, okay, duration was actually increasing the bad score, so it was not a good thing that we asked for 48 months actually. Nevertheless, 4 years to pay it back. We see that also the sex was also impacting a little bit. That's of course not a good thing, that maybe amounts to some kind of discrimination already. For how much it was asked and for the purpose was actually not too important, and that she was owning already his own house or apartment, whatever. And it was actually a good thing, right? It decreased the bad scoring. So let's do that a bit more complex and see how these different kind of things interact with each other. So here we have now a 2-dimensional ice plot. So more as we see now the surface of the original model. So we have F hat here and G hat over here. So we see that that's because of the RBF kernel and so on, fairly complex. Of course, that plot would help us already a bit. Nevertheless, it's not really good to interpret because it's, you know, it's not a linear one. Right now, our G hat, you see it's super linear, the way we constructed this by definition, right? And we see nevertheless around here in that area, it looks fairly similar to what we're seeing here, right? Also, the histograms actually for the marginal distribution of the training data, it looks fairly similar. So it's doing a fairly good job, right? So in the local proximity, well approximation. And we can see, for example, that here changing the duration is having a big impact, right? That's changing the prediction going from light blue to dark blue. But going in that direction, that's the credit amount, it's not changing too much actually. So it's not super important actually. Of course, we could also do line for text data. It doesn't have to be this kind of tabular data as we have seen before. And of course, if we now have raw text, we need first to translate it somehow to a vector representation. And we could, of course, do that like a bag of words and so on, saying we have these two sentences over here. This text is the first and finally is the last one. And then we simply count, okay, in the first sentence, this is once in there, text is twice in there, is one in there, and so on. Right, we can also do that for the other. This is once in there, text is not in there, is one in there. Here we have finally, the other we had not finally, right? And so on and so on. What we can do sampling randomly set the entry of inverts, setting the entries of inverts to 0. So more now trying to remove stuff, right? That's often the idea. If you're not talking directly to tabular data, but more structured data, you try to move something from your input. So for example, what would happen if finally would not be in the second sentence? And that's really then equal to removing all occurrences of this word in the text. And what would happen, right? That gives you some intuition now. Proximity could again be an exponential curve with cosine distance now, which is nice and very common actually because it neglects words that do not occur in both texts and measures the distance irrespective of the text size. So let's do that a bit more concretely. Let's say we've trained a random forest classifier labeling movie reviews from IMDb, a very famous movie rating review database. And let's say there are negative reviews and we have positive reviews. Our surrogate model, our local surrogate model is now a sparse linear model. And now we can check actually what is the impact of certain things. So that's maybe we had some kind of review for our first prediction and we were seeing actually, okay, that was a really negative review. And what we're seeing, what is the reason for that actually, why it was classified as negative, it was using words like worst and waste and bad and awful, right? And then there is one review which is counted more as positive. And when seeing then something like words like best, great, perfect, and so on, they're having a positive impact, whereas actually a word like plot was not having a good impact. But overall, you can see what kind of words really matter for either being recognized as a negative or positive review. We can do more of the same idea now for image data, right? So each observation is now represented by a binary vector indicating the presence or the absence of superpixel, right? What you can also do is trying to remove that. Maybe from one of the first videos you remember the Husky example. It was exactly this line. Superpixel, why are we talking about superpixel? Because these are interconnected pixels with similar colors. And the idea is that the absence of a single pixel might not have a strong effect on the prediction, right? But if you're moving here really entire patches of these, at some point we're really losing information. The problem, of course, is what is the size of the superpixel? And these have to be determined by the user. And that's a different kind of story, right? If I'm moving these very small one, or if I'm moving these kind of parts, or if I'm really going for larger pixel, right? So we really see different kind of super pixel sizes, sorry. And then what we're doing is the sampling for generating Z again. Randomly switching some of the superpixel off, so simply trying to remove them, simply turning them gray as I did here, right? Overcoloring them. So here an example actually, that's again an image predictor. I now try to predict what was actually predicted and why. So what we were doing is actually carrying out all superpixels with size 10 of these, so that some information is still in there, right? And the surrogate was a local weighted sparse linear model. And what simply is everything is more or less integers, right, for colors and so on. It was simply an exponential kernel with a Euclidean distance. What we're seeing, for example, if we'd like to explain why is there an electric guitar in there, then maybe that part of the image was important. If we would like to see why it could be maybe an acoustic guitar in there, yeah, that part would be important. And whether that's an upper door in there, of course, here the head was the important part. Why Lime was not going for that part, I don't know.